Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, welcome to the 12th lecture of the course Maritime Structures, Types, Construction, Pre-Service Analysis and Design, hosted by Department of Maritime Engineering at IIT Gandhinagar. In the previous set of lectures, we discussed about different types of offshore platforms, their geometric design, their applications, their functional use, materials of construction, to a greater extent the location of installation and depth of water installation, etc., along with their types and classifications. We have also understood the structural action of these kind of structures which are subset of maritime structures. Furthermore, we also went down to understand different kinds of coastal protection structures which are also part of maritime structures which are constructed for various reasons at various locations along and normal to the coastline to protect the coastline for strategic reasons. We also learnt how one can install temporary platforms for rescue and emergency operations, including some kind of regular maintenance works which are generally carried out on ship hulls and offshore platforms like painting, gunniting, repair, rehabilitation, strengthening, etc. Extending this understanding further down the line, in this lecture, let us make a discussion about wave energy harvest systems. Wave energy being one of the important segment of green energy and blue economy has becoming a very important note of countries like India. Of course, wave energy harvest systems are not only proprietary item in Indian Ocean, but of course many international countries also start investing on harvesting energy from wave and wind. Especially when you talk about wave energy harvest, a robust offshore system design is required to be commissioned to harvest wave energy on the coastal sites or sometimes deep ocean as well. In this lecture 12, we are going to discuss about bio-inspired offshore floating platform, which has been a very good contribution by Dr. Patil from Karnataka. So, credits to Dr. Basanagoda Patil, who had intensive work on design and development of a bio-inspired offshore floating platform, which I will discuss for the benefit of academic interest of the viewers. So, friends, welcome to lecture 12 on wave energy harvest systems. It is the first lecture in the series which will talk about the design, development, experimental and analytical studies carried out on bio-inspired systems used for wave energy harvest. A multi-utility platform is being conceived, developed and designed and named as Suzuka Dolphin. Suzuka stands for multi-utility functions, namely tsunami protection, solar power utilization and coastal applications, which has been a trademark patent granted, an Indian patent granted, as you see the details on the screen. A typical bio-inspired system like a dolphin fish looks on the screen. So, it has got a configuration similar to like a fish. The tail and the mouth of the fish are used for different purposes here. The tail is being tagged to a power takeoff mechanism through which the oscillatory motion of this Suzuka dolphin is harnessed to get electric power, while it is connected to the base block on the coastal side of the platform. Whereas the tail is being used for power harvest, the front end of the float, which is the nose of the dolphin, is fixed with the floats, which makes it buoyant. So, under the wave action, these floats will lift the dolphin in the upward direction, and these structural members will start having rigid body motion. Because of this, the bottom flip flap action, and that will cause the hinged connection motion, where a PTO mechanism is connected to this, which helps me to harness the energy. So, friends, the multiple utility of this platform goes like this. It produces power from sea waves with a better efficiency. It can also offer a tsunami protection. We will talk about that slightly later. It can be helpful in generating solar power from open sea. Can also be a good source of recreation, and tourism center can also provide a training center for people suffering from seasickness. Okay. So, the body of the configured platform, which is completely floating, looks like a dolphin, therefore, the name dolphin, and Suzuka refers to multiple utility functions, as you see here. The idea is originally conceived, tested, developed, designed and then product configured at IIT Madras. So, friends, let us look at the different working models of Suzuka dolphin. Let us look at this model first. The nose of the dolphin has series of floats attached, because of the buoyancy action of these floats, the nose is lifted when the waves come and approach this dolphin nose. So, the up down movement of this will cause a hinged connection here, will make the dolphin to rotate up and down at this hinge point. This rotation will start this piston and the rod will get into the piston, and this linear motion will now help me to harness the wave energy. So, rotary motion is converted to linear motion. Okay? That is the concept what we are following here. Now, the hinged connection helps me to lift this at this point, which is pivoted at this point, and then this lift will help movement of this piston into the cylinder, which helps me to produce current by electromagnetic induction, which I will show you later. So, there are other assemblies present in the dolphin body, which is helpful to harness this energy apart from doing this. This is one way of action which helps me to produce wave energy. Let us look at the second one. When the waves of very high amplitude approach the dolphin more or less stands vertically, okay, more or less stands vertically, and when it stands vertically, it becomes like a temporary seawall. We already know what is a seawall. It becomes a temporary seawall protecting the shore from the tsunami waves. So, it also acts as a temporary protection during tsunami. However, after the tsunami recedes, this becomes a lock which does not allow the dolphin to float back. So, it is a one time use, a standalone function where once lifted is locked. So, it cannot come down. So, the body is designed in such a manner, the structural strength is certified in such a manner that it can withstand the lateral forces caused by the waves. So, second action is tsunami protection partially. The third one, on the body we also put some solar panels which is kept on the open sea, which can also be connected to the generator unit, which can help me to harvest the solar power from thermal radiation effects. So, when I start providing this kind of dolphins in series, I can connect the power grid and start giving supply of power to the coastal systems around in case of any emergency. It is not a regular supply, but this can be useful for giving a temporary supply for a short time in case of emergency requirement of coastal tide structures. So, it has got different functions: wave energy extraction and production, solar energy extraction and production, tsunami protection partially, and also gives training for people on this. For example, all along the surface of this, one can also have chairs where I can draw it here if it's comfortable, I can draw it here. So, I can put a chair and we can make people to sit here. As the dolphin moves up and down, a seasickness training can be imparted to these people. Okay. Can also be a recreation center for children to play around, because it is connected to the coastal side and one can access this to the top, and the typical dimensions of this dolphin I will show you. So, typical dimension, the length of the body is about 30 meters, it is fairly long. Okay. It is connected to the deck, which is about 15 meters, where it is hinged here at this point. Every float of 1 meter dia is attached to the nose of the dolphin, and the draft level is kept in such a manner that about 40% of the dolphin body is in water. So, it allows me to give positive buoyancy to the float. Okay. The overall dimension of the body varies: 2.88 at the nose, 5.77 near the belly and 4 meter near the tail. So, this forms approximately a shape of a dolphin. Okay. So, these preliminary dimensions of so-called dolphin are based on the studies conducted by me with my research team in 2022, which are published already in different international journals. Let us look at the equation of motion for our understanding how this was modified and modeled numerically. The equation of motion of the body, considering only the heave mode of operation as active degree of freedom. You know, the Suzuka will start moving in the vertical direction as up and down. Let us say if I consider only that as my heave motion, of course this is connected to, or it is coupled to the pitch motion here. So, the independent degree of freedom is the up and down motion, which is written by this, where Fe stands for excitation force acting on the body, Fr stands for radiation force of the body, and Fb stands for the buoyancy force acting on the body. So, algebraic sum of these forces are equal to the inertia force excited by the Suzuka dolphin body. The rigid body displacement conforming to flexural deformations in the body are considered to be negligible. Therefore, I can now write or convert this equation of motion into the rotational degree of freedom theta, which is the pitch action here, as you see in this equation here. Okay. Once a numerical model is developed, analytical study is also carried out, and a numerical model developed in ANSYS Aqua, and one can see the model here with a dense mesh appearing on the screen here, okay, with all the connectivities happening as you see here. The natural frequency and damping ratios of this dolphin are as seen in the screen. It is about 0.55 radians per second with a damping ratio of 4% in heave, and 0.8 radians per second with 2% of damping ratio in pitch motion. So, one can also see the free float RAO of heave and pitch degrees of freedom. It is clearly seen that both heave and pitch, which are coupled each other very strongly, gives me two peaks, whereas near resonance level or at about 1.1 radians per second, they have a very strong dip. One can notice that almost both degrees of freedom gives me the peak value at more or less the same frequency ordinate. That is the beauty of the design. Though these two degrees of freedom are coupled and though they have a different natural frequency, but the system is designed in such a manner, the buoyancy and the body geometry is adjusted in such a manner that the peaks appear more or less at the same frequency in both degrees of freedom. It means the body is now able to harness energy maximum either in heave or in pitch or both by the same frequency ratio. So, the tests carried out were commissioned at 150 meter water depth, keeping the mass and other details as you see in the screen here, and this work is already published in Journal of Marine Science and Technology in 2025. So, for more interest you can see this paper and get more information about the technical details of the results of numerical study carried out. Friends, in this screen let us present the heave power spectral density function of two different results. One is a 5 meter and 11 meter waves of irregularity in nature. So, the irregular wave has got about 0.4 to 0.81 radians per second frequency, whereas the regular wave had a frequency of 0.6 to 0.7 radians per second. So, one can see that this line indicates the natural frequency of heave. For a 5 meter wave, the peak frequency appears here. So, one can see that the power spectral density function of the Suzuka dolphin is able to amplify the peak closer to the peak frequency of the wave to a near resonating condition. So, this is a general requirement of any wave energy harvest design system to capture or to harness the maximum energy possible which is encountered by the body. However, there is a shift and this peak does not happen closer to the natural frequency of the system in heave direction, so that failure of the body is avoided. Okay. Let us look at the pitch degree of freedom. This is the heave frequency what we notify here, and this is the peak frequency of the wave, which is 11-meter wave now. Okay. So, one can also see that the peaks happen closer to the wave frequency, whereas at the natural frequency of the heave, the system does not resonate at all. So, the design is configured in such a manner, the body geometry is distributed, the mass is distributed in such a manner that it does not happen at the natural frequency of heave degree of freedom. So, if you look at the pitch response, the angular displacements, it is maximum at 11-meter wave height, which is about 74 degrees, whereas it is minimum for 5-meter wave height, which is about 40 degrees. So, this degree what I am saying is this value, is this oscillation, this oscillation. This degree is what we are saying. Okay. This is a very interesting plot where we wanted to ascertain the control and response. You want to really redesign the system for any failure. This is a quadrilogarithmic plot used for heave response of Suzuka. So, it has got all the 4 axes plotted. The horizontal axis refers to frequency ratio, which is excitation frequency by natural frequency in heave degree, because it is a heave plot. The vertical line refers to pseudo velocity. This axis refers to pseudo displacement, and this axis refers to pseudo acceleration. So, since there are 4 quantities represented simultaneously like velocity, displacement, acceleration as a function of frequency ratio, we call this as quadrilogarithmic plot because they are plotted in log scale. Let us understand this curve more closer. So, there are 2 colors what you can notice here. One is the input wave spectrum, which I am marking here, refers to input wave spectrum. The other one is a pseudo heave response spectrum, which I am marking here. So, this result is now projected on the screen for 11-meter wave height and 10 seconds period, which is closer to 11-meter wave height is a very big amplitude in irregular sea state. Tsunami is about 17-meter wave height. Okay, it is a very closer. So, we conducted this test on a scaled model and plots are arrived. So, this is my input spectrum, this is my response spectrum in heave degree. So, if I take any point on the response spectrum, and start projecting this point perpendicular to displacement, velocity and acceleration, I will be able to get the control points of these data, which is useful to design this particular system. Okay, that is the use of this particular plot. So, the equations are available on the screen and the full detail of this is available on Journal of Marine Science and Technology paper. Let us discuss about this particular plot for interest of the viewers more. The horizontal axis represents frequency ratio, whereas 3 axes, the vertical one represents pseudo velocity and inclined axis represents displacement and pseudo acceleration respectively, as I discussed. So, therefore, the plot shows pseudo response spectrum, and it is very clear that the pseudo response spectrum clearly exceeds, the peak clearly exceeds the input spectrum. This is the fundamental requirement of any wave energy harvest device. If it is a building or any other structure, then the response spectrum peak should be within the input spectrum peak. Whereas for wave energy harvest systems, the response spectrum's peak is expected to be higher to harness the maximum energy. So, this is higher than the input spectrum peak, as you see on the screen here. So, it is much higher to give you the maximum harness condition. It helps us achieve sufficient heave motion to assist vertical lifting during high tides. So, one can also see at beta equals 1, beta equals, that is 0.975, one can see this is 1, the peak is just closer to this, okay, it is not at 1, okay, you can see here. This is the line 1, the peak is here. This is the line 1, the peak is here, is about 0.975, closer to 1, okay, it is not 1. So, it is closer to 1 and the peak of the input wave is about 0.1, see here, is about 0.1. So, peak of the input wave is different from the peak of the spectrum, which facilitates that even though there is no resonance happening, the wave energy harvest is maximum. That is an advantage in the design. Okay, it is at 0.1, whereas this is at closer to 1. You can see the response peak is shifting towards the left, indicating that it is a stiffness dominated response. Once the system is stiffness dominated response, one can easily tune the stiffness parameters to control the response or to design the system to be more rigid. By selecting a point in the response spectrum and projecting them the different axes, one can also find out the contributions of these plots on different scales of velocity, acceleration and displacement. So, this can help designers to have an insight about the inertia, damping and stiffness influences on the design, because I am able to get the influence of this point on displacement, which will help me to stiffness influence, velocity, which helps me to understand damping influence, and acceleration, which helps me to understand the inertia influence of the design. So, quadrilogarithmic plot, as discussed in the previous slide, helps you to understand the design perspective of this new developed Suzuka dolphin in dynamic perspective. Therefore, this serves as a powerful tool for response tuning and performance optimization for such kind of devices. Having said this, let us look at the studies conducted on experimental scale of this. So, let us see how the power was harnessed from the motion of this body. Let us say two dolphins are connected in tandem, parallel. Can you see this piston cylinder assembly which are connected to the base of the platform? This is the platform, okay, this is the platform which is fixed at the bottom on the sea coast in the laboratory. So, these are connected to this system, and if you enlarge this, it looks like series of moving rod into the cylinder. Okay. These rods move to the cylinder. When these rods move inside the cylinder, the electromagnetic flux is interfered and that creates current. So, how this rod is moving? Very simple. When the wave hits the dolphin nose, dolphin lifts. When dolphin lifts, this hinge will try to enable the dolphin lift. When it lifts, this piston rod goes in or out, okay, goes in or out, and this linear motion is making electromagnetic induction carrying here that generates power. Okay, that is how it is done. Let us look at a video of this later. An extended view of this particular assembly is shown here. Okay. A steel rod moves into the cylinder and the cylinder contains the neodymium magnets in between, and the rest of these parts are with non-magnetic material. Okay. An assembly is made with a copper winding done at these areas, and the electromagnetic flux induced because of the motion is helping me to create current, which is measured using a multimeter. This is already published in Ocean Engineering and Marine Energy Journal. Those who want to have more details about the design configuration, please have a look at this paper. Let us look at some analytics of this experimental power generation happened. The instant wave power can be given by this equation. The instant wave power can also be a sum of this captured with instant and WC. The electrical power then can be computed using this equation, and efficiency can be worked out using this equation. If one is wanted to find out under irregular wave instant potential, one can find the instant power, power absorbed by Suzuka, and hydrodynamic power efficiency using these equations. So, these calculations and details are presented in Journal of Ocean Engineering and Marine Energy, which can be read further to find out more information about the power generation calculations. So, let us look at some of the components and steps involved in this experimental study. So, when the wave hits the Suzuka dolphin model, the nose moves ups and down. So, Suzuka dolphin moves up and down under the wave action. Okay. So, this will induce a motion about the hinge and it gets lifted. This will cause a to and fro motion of LMEG. Okay. LMEG, that is the cylinder and the piston arrangement. The piston will get into the cylinder up and down, that will create the electrical energy by electromagnetic flux induced in the system. Then the steel rods having magnets moves to and fro inside the hollow cylinder, and the magnets are placed at these locations, whereas between locations are with non-magnetic material. Furthermore, electromotive force is generated, EMF is generated due to the movement of this rod inside the cylinder, and that causes the electric power generation. Okay. One can also look at the heave power spectral density function and the power absorbed by the LMEG for a simple 5 centimeter wave at 2.5 seconds period. It gives me an efficiency of about 31.54 hydropower and about 30.07 electric power, already published in this journal. So, under irregular waves, a similar efficiency calculations were performed and hydropower was about 33% and electric power is about 32%, published already on energy paper in cited here in 2024. So, one can see this paper for more details. We also have something called the Bode plot, which helps me to compare the theoretical and experimental frequency response of Suzuka. What is a Bode plot? Let us look at this plot. Bode plot are actually frequency versus magnitude and phase angle, magnitude in dB and phase angle in degrees. Bode plots compare the theoretical and experimental frequency responses of any system of your choice. It is able to harness and understand the second order dynamic effects of the system. Okay. The frequency response function is given by this equation. Let us look at this plot first, the magnitude versus frequency. So, there are two lines plotted here. The blue one indicates theoretical using boundary element method, and the red one indicates experimental of the specific model, scaled model. So, what does it tell me? The magnitude plot shows me at low frequencies, that is from 0.1 to 1 radians per second, 0.1 to 1 radians per second, that is this region, okay, this region, both theoretical and experimental are matching with 0 dB, right, it's closer to 0 dB, correct, signifying consistent system behavior under long period wave excitation. When you increase the frequency, when it goes from 1 further, a distinct response peak appears at 1 to 10 seconds. The response peak appears at 1 to 10 seconds in this here, okay, 1 to 10 seconds radians per second, with a theoretical response reaching about 20 dB, okay, 20 dB, signifying high sensitivity and enhanced energy capture near resonance. The experimental results follow the similar trend as per the theoretical. Okay. So, when you look at the phase plot, it gives me the sharp roll off, confirming sharp roll off. For example, both the responses, there is a sharp roll off exactly at this level, and there is a change in phase, okay, confirming that Suzuka dolphin effectively attenuates high frequency excitation, contributing minimal to the wave energy extraction, thereby improving the structural stability. Okay. So, the system is stable, system is also able to compare with its theoretical results, and system is able to also behave well in a consistent manner for long period excitation waves. Having said this, the phase plot clearly confirms that there is the strongest agreement between the experimental and theoretical results, and the Suzuka dolphin behaves in a very nice manner by agreeing on theoretical and experimental manner. The phase plot at low frequencies remain closer to 0, okay, at low frequencies, indicating in phase response with instant waves. As the frequency increases, the phase transmission happens rapidly from 0 to 90 and 90 to 180, 0 to 90, 90 to 180. The experimental phase response closely follows the theoretical trend, as you see here. So, this phase transmission rapidly changes from 0 to 180, causing a nice roll off and confirming that the structure is stable even under this kind of behavior. To understand this further, we also conducted something called failure mode effect analysis on the system, which is a combination of 3 parameters: severity, occurrence and detection, to find out the risk priority number. So, the risk priority number indicates very high digit in terms of dolphin buoy with the most susceptible component of this system. So, rigorous testing in the lab is required, and the buoy should be designed bodily to resist this kind of wave action. The second component, which is more vulnerable, is LMEG, which is used for power generation in the piston. Okay. So, the recommended actions for this control risk analysis is use high end cables and check the power output at frequent intervals of time. So, FMEA study was also carried out at 2 locations. One is slider crank mechanism, other is Scotch yoke mechanism, which are 2 power takeoff assembly recommended for this kind of system. A slider crank mechanism is having a crank and a crank wheel and a connecting rod which helps me to move this, and assembly is generated or power is generated from this rotation. Whereas, in a Scotch yoke mechanism, then there is a yoke and a pin arrangement here, which is attached to a rotating wheel, and the power is generated from here. So, we have also compared the study with crank mechanism and yoke mechanism. The results are given here. One can see the failure probability. The mean time to maintenance point is a part of this particular system, which will help you to understand the failure modes. Look at the failure modes. The buoyancy loss happens about operation of 6,300 hours. Okay. After operation of about 6,000 hours, the buoyancy loss can happen. So, about 6,300 hours, the buoyancy fails on a float, whereas the failure probability closely reaching 1 is happening only on the magnetic rod fatigue and the buoyancy loss. These are the 2 components which has a very higher probability failure. Okay. So, when you use LMEG, when you use a PTA mechanism based on crank arrangement, then the failure probability is more for a crankshaft fatigue and the joint failure, whereas this arrangement happens at a working pin fracture of 7,000 hours. So, the failure mode or the mean time repair, the mean time to maintenance is about 7,000 hours of working. So, the study also helps us to understand at what frequency intervals the system should be inspected and maintenance should be carried out. So, friends, Suzuka dolphin is an effective method of generating power under regular and irregular waves using linear motion electricity generator. The maximum electrical power efficiency is about 30% and 32% for regular and irregular waves. The regional assessments show that the device can consistently absorb power in Bay of Bengal and Arabian Sea, insisting on made in India concept, which has been developed and tested as proof of concept in India. The BioInspire platform and its performance confirms the proof of concept which can be used for Indian sea states. Now, let us quickly see how the video of this platform a behavior looks like. So, friends, as a summary, let us try to understand the important points of the design. A BioInspire platform useful for harnessing wave energy and primarily and other multiple functions is discussed. The complete design, data, results are patented and published. So, you can refer to those references for more details. For more details, please see these references and try to learn more details about the specific design. Thirdly, friends, the wave energy harvest system, which is essentially a made in India concept, is important for creating green and blue economy in maritime industry. Hope this design helps you to at least start with the type of problems which can be designed and developed for our wave energy harvest in the near future. Thank you very much. Namaste.